All right, good morning, everyone. Welcome, and happy to see that many people here this early in the morning. I'm glad I made it myself, so that's actually quite a luxury. Welcome to the Async Programming Deep Dive talk, which is really something, to look behind the scenes of how the async features in C# and Visual Basic are implemented. Also talking a little bit about some caveats and, common use patterns and extensibility points. So without much further ado, I actually had some deep debate yesterday night. Should I go for, the death by slides in the morning, or should I do something to wake people up? And I decided, well, why not serve some breakfast menu and actually let the people once more decide what we will be talking about, because there's so much we can talk about in terms of async. In fact, I could be standing here the whole day and sort of like look at all the nuts and bolts of how it works. So we have to make some natural selection here. So I divided it into a number of different sections over here. We have some starters, which I don't necessarily consider to be lightweight, some light starter. Instead, it's more like fundamental knowledge, so that you sort of have the framework to think about async methods and how they actually execute. Then we have entrees. I'll be talking about a bunch of, interesting things. I could highly recommend a couple of things in there that are really to sort of blow you off your socks. Things like stack spilling are very, very fun, and, awaiting dotnet events is some nice extensibility point with awaiters. Then we have some desserts. We have things like task combinators, exception dispatch info, little things that are in the framework, really lightweight, that you may not be aware of. Finally, some new dishes. C# 6.0, we have support to await inside catch and finally blocks, and the compiler is doing quite some voodoo there to make that work. It seems more complex than at first you may think. And then some chef secrets that, in fact, we may be talking about in between sentences here and there as well, in particular execution context, and maybe something else that comes to mind during this lecture. So let's get started. Why doesn't somebody pick a small starter for me? The state machine. A classic, let's start with the state machine. Good. So, in fact, I'll be talking about async method builders as well, because to get to the state machine, I need to show an async method builder as well. So, let's actually take a look at how the compiler transforms an async method. Because, well, as you can already imagine, the CLR doesn't support methods that can get paused in the middle. You're awaiting something, it's not done yet, you need to pause the method. Well, there's no magic in the operating system or the CLR to say like, oh, stop processing here and I want to reuse this thread for something else. We need to do something with everything that's on the stack, and we need to basically evacuate the house and let somebody else occupy it to do, for example, UI processing. So there's a whole bunch of things that need to happen there in order to make that work. Now, if you already are familiar with things like iterators in C# 2.0, they use pretty much the same technique to make it possible to write a logical control flow using a whole bunch of yield returns and yield break statements and loops and everything you can think of, but make it possible to execute that logic through the course of multiple move next calls. Like you call move next, it runs to the next yield return. You call move next again, it goes to the next yield return. That's also a pausable method. So the technique is very similar in that basically the compiler will divide and conquer your method into different little pieces that then become part of a big-ass state machine. So let me call this thing state machine demo, just to start with that. And let's start off with taking a look at the simplest possible async method we can think of. Actually, really the most trivial async method. Static async foo async. With a void here, that would be kind of comfortable. Well, that's the most trivial async method that you can imagine, right? Like, it's doing nothing asynchronously. That's kind of super lazy. But, it's totally valid, and the compiler complains, oh, why are you making this thing, async? There's nothing to await in here, like, but we'll compile it anyway. And the way that will get compiled is actually already by generating some types. So let me go and build the same thing, but without the async modifier. And then we'll start sort of building up this method a little bit to make it more complex. So the compiler will create an async foo async method, and I can't overload just by async modifier. So just imagine that the 2 is not there, but that's what the compiler does with the method. But since it's an async method, it needs to use some helper types. And really there needs to be something that governs the entire state machine, like everything that's happening in that method beyond the wait points, waiting for something, resuming, all of that stuff. There needs to be a party in charge of that. And that's going to be the state machine. So compiler will generate a class. Oh, actually, oops, first mistake. Compiler will generate a struct that implements an interface called async state machine. And that thing will have an unspeakable name that I can't type here because Visual Studio will say it's not a valid C# identifier. We'll take a look at it in just a moment. But let it just call me that thing foo async state machine. Okay? And that implements async as state machine, which comes from the system runtime compiler services namespace, where there's a whole bunch of little, tools and utilities that are actually useful to take a look at sometime and wonder, like, which compiler is emitting this under which circumstance? Like, that's a popular activity to do in the weekends, right? Just browse some namespace that you don't have any business with, really. Now, if you look at the async state machine, what's in there is a couple of methods. Now, the second method, I'll sort of skim over that. We'll get to a little bit more detail about the set state machine. Because, like, why does the state machine need to have a set call for the state machine itself? And the reason there is some optimization. First of all, you can notice that this thing is a struct. Now, when an async method runs and it needs to pause at some point, well, structs by default live on the stack. But, when you're pausing the method, you need to evacuate your stack because somebody else is going to move in the house and do stuff. So you can't leave your stuff on the stack, you need to move it to the heap. But because we start off with a struct, by default, if your async method never has to wait, we don't want to spend any time, with dealing with allocations on the heap. So by default, this whole state machine is actually a struct. So at the point in time where your method actually pauses, we need to move all of that stuff from the stack onto the heap. In the worst case, when the thing pauses. Otherwise, we won't bother doing that. And that's why, there are some additional methods like set state machine that get called only at the point in time where we have to evacuate stuff. So let me just ignore that for just a moment here. But let's continue here by taking a look at what it means to create a method that has an async modifier. Well, obviously, I've created a state machine. The compiler has generated that. And the state machine needs to be created, right? So let me call, the constructor on that thing to create a new foo async state machine. So far, so good. Now, who is going to drive that state machine forward? Like, every time, that method resumes, it needs to do some stuff. Well, in this case, it's quite an empty method, so there's nothing to do, but still, you need to have all the machinery set up. And the way the machinery gets set up is by creating an async method builder. So what's the method builder look like? I'll just create it here, method builder. And it's also in the system runtime compiler services namespace. It's an async, and you can see there are 3 different ones: an async void method builder, an async task method builder, and an async task method builder of T. So if you have 3 different, signatures, void, task, or task of T, it will choose a different type here. And in just a moment, I'll switch over the void to task, and we'll change this from async void method builder to async task method builder. Now, if we take a look at this type, just very quickly, we can see once more that this thing is a struct. So by default, we are not paying any price to go to the heap and have garbage collection of a lot of objects. Like, everything sort of stays on the stack till the last moment in time where we have to move everything onto the heap. In this case, we will never have to do that, simply because my method is not doing anything. So what's the last thing here? Well, this method builder has to live somewhere. Now, where do we want to use that method builder? The method builder is going to be used in the move next method over here. Every time we have to await, every time we have to return, every time we have to throw something to our caller, we have to go to the async method builder. So I better have that thing available over here. So how do I make it available? Quite simple. I'll just, go here, add a private field of that particular type, okay? So I'm just going to put that over there, and then we can do state machine dot method builder equals that particular thing. And because it's compiler generated, it will be just a public field. Nobody can access it anyway. So, like, why bother creating properties and all of that stuff for that? Now, the final thing here is, well, we have to set that thing in motion. How do we start that thing? Well, maybe there is a start method on it. Let's take a look. Method builder dot start. Oh yeah, there is a start over here. And the start, once more, is super careful not to allocate anything if like not needed. So it takes in that state machine by reference over here to say like that's where the state machine is, and it's just a reference to something on the stack. And if that thing comes to the conclusion at any point in time that this thing needs to evacuate to the heap, it will just use that reference to pick it up and move it into a field somewhere in something that can outlive the async method synchronous invocation. Like when you call it, the stack is still there, but when it has to pause, it needs to basically get rid of it. Now, we have the set state machine over here, which will not be called yet because I'm never going to await anything in my method, but I still have the move next. The move next is where, finally, the state machine will live. That basically governs where we are through the execution of the async method. If we have many awaits in there, we need to know, well, did we wake up because the first await completed, the second one, the third one? Like, we need to sort of know what the instruction pointer is of our async method. In this case, there is nothing. Well, there's one thing to do. That's actually go to the async method builder and simply call setResult. And setResult means or signals the async method builder that the method has done working. So that's as if, you have a return statement over here. Anytime you see a return in an async method, the compiler compiles it into a call to setResult. Now, of course, in this case, it's void, so seems like there's nothing to become the result. But still, we need to know that this thing has finished execution, that it can't re-enter the state machine and do all sorts of fancy things, like it's the end of it, okay? So that's over there. Now, that's really how this thing compiles. In fact, I could try to run it. And async void is not the best thing to do. I'll talk about that in just a moment. But let me just do foo async 2 over here and just call, well, I can't call wait on it, damn it. That's why it's not good to use async void other than for event handlers. So here we go. We just call foo async 2, and let me just set some breakpoints here and see what's happening. We create our state machine, we set the field, we call start, and start has dispatched, as you can see, into the move next call. What's happening here? If you look at the call stack, you see that internally the async method builder start calls move next to kick off the state machine. Now in this case, the state machine is quite lazy. It doesn't do too much. It simply calls setResult, and this thing just returns, and the async operations have finished, because there was nothing to do. So let's make it a little bit more complex, of course. How can we make it more complex? Well, let's first of all start by making this thing return task of int, okay? So that we have something meaty to return to our caller. Now, when this thing is task of int, like this, well, how do we return from foo async 2 now? Well, of course, I can't return nothing anymore, I will return 42. So how do we return from foo async 2? We need to return a task. Guess what? The method builder is the one responsible to create tasks for you. Don't have to deal with task completion sources, all of that stuff. Compiler doesn't want to know about that. Compiler just says, give me one of those method builders and you will do everything for me. You will do the dirty dishes. Okay, fine. So we can go to that method builder over here and we can ask it to give me a task. Well, there's no task here. Why? Because I'm still using this async void method builder. I better use the async task method builder of t and call create on it like this. Okay, so here we go. We have an async task method builder of int, and things start complaining, obviously, because this type also has to change. But now this thing can return to me a task of int that indeed will govern the eventual completion of the method. How does that thing complete? It completes at some point in time when the state machine reaches a return statement. And in this case, it's return 42, so it becomes setResult of 42. Okay, so quite easy. There's still no state machine here. Well, because I'm writing lame async methods just to sort of set the scene. But now when you execute that thing, well, I can change it a little bit. I can call result on here, right? I can call result and I can do console.writeLine of that whole thing. And now we can actually see exactly the same thing working. But now there's already something interesting going on. As you can see, when we call start, move next sort of starts doing stuff. But at some point it may get stuck because it's awaiting something that's not done yet. So at that point, move next will return, start will return, and we can simply return the task to our caller. without being blocked waiting for the asynchronous operations to finish. So in this case, nothing special happens. When I just hit F5 here, same thing, everything will run synchronously because I'm calling setResult immediately, and by the time I get out of here, the task has already completed and it contains the value 42 already. You can see ran to completion result 42. The async state machine or the async method builder is the one that owns the task and the completion source and will set 42 on the completion source, making it finish the task. All right, so far so good. Now let's do something real, where the state machine comes into the picture. So now, we can sort of fasten the seat belts and take a look at what's going on. So let me start by just wasting some resources here by simply doing a task.delay. I'll make it long enough so we can see the effects of the asynchrony here. So, let's just wait for 10 seconds. Now, where does that code go? I'm done with the foo async 2, by the way. That's all the compiler generates for the method that you wrote. All the rest goes into the state machine. Like anything you do with if statements, while loops, using statements, whatever, all of that stuff moves to the move next, okay? So foo async 2, well, we don't really have to look at it anymore. I'll just keep it there with a breakpoint so we can inspect, the asynchronous behavior in just a moment. So now we have return 42, which compiles into setResult. And on top of that, we should have the code that does the await. So how do we do the await? Well, first of all, there are two stages in the execution of this method. That's really the mental model you should take in mind. It's like when you see an async method, start counting the number of await statements. Well, not statements, expressions. That's where the stack spilling will come in later. Awaits are expressions, they're not statements. They don't have a semicolon at the end. Often they have because users are kind of lazy. But they're really just expressions. They have a value. If you await task.run 42 or something, you can add that thing with something else. You can do a plus operator. But so, in this case, we have one await. That means that there are two states in our state machine. The code that runs up to the first await, and then the code that runs after the await completes. So I need to have something to remember where I am, because this move next will be called many times. It will be called initially, as we've seen, when we start the state machine, but it will also be called when the delay eventually completes. And I need to disambiguate, well, do I still need to start the delay or do I need to continue from the delay? So we have to introduce over here some field that's the state, okay? And that will be just like an instruction pointer. So now when we enter move next, initially the state will be 0. In reality it will be -1 or something, like compiler starts with different numbers there. But I'll just be lazy and start with 0. What it will generate here is a set of if statements, or in general it will create a switch statement. In this case I just have two states, so it will actually become an if statement. If the state is 0, I need to do something, and if the state is 1, I need to do something as well. And let me just, not really do exactly what the compiler is doing, but I will only do one thing per state, okay? So in state 0, that should be the code up to the first await. And then state 1 should be the code after the first await. Now, what am I doing after the await? If I collapse this thing so we have a little bit more room here to breathe, we see the first thing is task.delay, and after that I need to return 42. So everything here, and sort of half of the await keyword, I should say, like, the thing that completes it, well, actually more the IT part, not the AWA part, like, the part that finishes the await, needs to be in state 2 as well as returning 42. So that's the second state. So let me move this thing in there, over here. Okay, that's good. So that's the second state. The first state, let me start eating at it from the other side. Okay, I need to call task.delay because it's the operand to the await. Clearly I need to evaluate that thing. So let me evaluate that thing by just doing copy-paste. Good, I've evaluated that. Now how does the await keyword compile? And here it gets interesting because there is no secret here. You can implement your own types that support await by just having exactly the same methods as the ones I will be typing here. So compiler simply desugars this await call into a set of method calls. And the first method call is, given the operand, call getAwaiter on it. I won't do the mandatory waitress joke here, or waiter joke, like, you've heard it many times, right? Like, this is not a sexist method, it's just, called a waiter, and it has nothing to do with bars or things. So what we get here is an awaiter, and what's that type of the awaiter? It's a task awaiter. That's nice. So what's a task awaiter? It's actually, once more, it's a struct. Why? Well, it could be possible that this delay of 10,000 finishes immediately. Well, kind of in this case, there should be cosmic background radiation in your machine or something for that to happen. But like, maybe you're awaiting a web request and it's already done by the time you're awaiting it. In fact, like, nobody ever said that you can't do, var t equals that thing and do some stuff here and then await it later. Like, by the time you're awaiting it, it may be done with sleeping for 10 seconds, right? Like, you could start a web request, do some other stuff, and then await the web request. Oh my God, I'm lucky, it's already there. Like, in that case, we don't want to allocate anything on the heap for that. We still need the task, that's enough. We already have a task on the heap, but we don't need other ceremony over there. So the awaiter type is a struct once more. So that's fine. But now, let's take a look at, once I have that awaiter, at some point, I need to get the result out of it, right? How do I get the result out of the awaiter? Well, at some point, you will call awaiter.getResult. Now, in this case, it's a void returning task, so the get result doesn't really do anything. But this would be a blocking call. If it would be task of int, it would return the int that the task eventually produces. Now, clearly, that part should not happen there, because then I'm stuck when I just do the equivalent of task.result or task.wait. So that needs to move somewhere else. And that's why I was saying, if you think about the await keyword here, you should think about one part that's sort of dealing with initializing the await, and one part that runs when the await is finally done. So that's the other side of it, or whatever you sort of want to slice and dice it here, but like you should think of it as the basic blocks sort of going through the await keyword. So let me just clean this up a little bit so it's shorter to read again. So this get result clearly doesn't belong in state 0, because that's the state where we start awaiting. That needs to move to the point of we know for sure that we're done with that particular operation. The asynchronous operation has finished. So that happens over there. But now you can already see, well, that the waiter, I don't have access to it anymore. I could move it out of the move next here into the global scope of the move next, but that's not really the necessary or the desired outcome. The awaiter needs to live across move next invocations. The first time you call move next, you have to start setting it up, and then you have to sort of asynchronously wait for it to complete. And then later you will end up back in this move next method to execute the second part. So this thing needs to move to a field, is the conclusion. Let me move it to a field, control dot, generate a field. Beautiful. So here's a field for my awaiter. Now it can sort of live across different invocations of move next. Now what's the next thing that await compiles into? The first thing is the lucky check. Sort of checking whether like, oh, are we lucky that this thing has already completed? So the compiler will generate, if the awaiter is completed, then I can move immediately to state number 1. So what I will do here is I will set the state to number 1. Because it's completed, I can call getResult on it with no harm done. It's already done, it will return immediately. So I will go to state number 1. And compilers are compilers, they use gotos and all of that kind of stuff. So let me just, sin over here for a moment and just create a goto. Okay? So we're just going to the next state. In fact, if it's a switch statement, it will be go to case that particular number. Okay? So we just move to the next block, and this thing now merrily and happily continues executing, and the result will be set. The other case, that's where the rub comes in. At this point, we're in move next, we're in the middle of doing something, and we need to evacuate. Because we need to return to our caller so it can do something else, but I should make sure that this awaiter eventually calls back and causes my state machine to go to the next state. So I still need to change my state to number 1 to be prepared for the next time I'm getting called, that I don't start doing the await again, right? I don't want to end up on this line again creating a second task.delay. I want to move on with my life to the next state. And this is where the last part comes in. What's the last part? I need to tell at this point to the method builder that I want to await the uncompleted state of my awaiter. Now there are two awaits over here, await uncompleted, await unsave uncompleted, and that has to do with flowing the execution context. We can go into more details later, but in this case task awaiter implements the unsave pattern, meaning it can optimize and it doesn't have to flow certain pieces of information which are expensive across async points. It will only flow it once in the method builder, so it will actually pick this particular method. What do I have to pass into that? I have to pass in the awaiter by ref, and I have to pass in the state machine. And this ref pattern is simply not the state machine attribute, ref this, because I'm a struct, I'm just passing myself to it. That's, the secret hand sort of coming from the ceiling and grabbing you up and putting you on the heap. That's why things are passed in by ref here. So inside the await unsave uncompleted, it will say, okay, we tried our best. We started with structs, everything looked good and rosy and shiny, unicorns, all of that stuff. But now we have to move all the way into the heap. So that's why the refs are there. So let's now take a look at how this thing executes, right? So let me hit F5 once more onto my foo async 2 over here. And I think I have everything in place. We'll see in just a moment. So as I go here, actually I don't have everything in place, we'll see that in just a second. If I F11 into start, we end up in move next, that's beautiful. And move next has state 0, and state 0 I get the awaiter for task.delay, oh my god, we're not completed yet. 10 seconds haven't elapsed, so I need to evacuate and take up my stuff and leave here. In fact, I could have waited on the is completed check for 10 seconds, and at that point you would see that I would be going through the different branch. Now when the method builder is instructed to await some awaiter here, it things blow up. Why do things blow up? Simply because I forgot something. I forgot to implement the set state machine method here. Whoops. Ah, fuck. I forgot to actually, sorry about that. I forgot actually to implement this set state machine method with the state machine that's passed to me. The thing I need to do here really is go to the method builder, sorry about that, go to the method builder and actually set the state machine on the method builder like this. That's again part of this hoisting to the heap kind of pattern, meaning like, this state machine was given to the method builder got it, now says like I need a place to store it. And we basically store everything onto that method builder, so that's the only object we need to keep on the heap. So the state machine is here being set onto that async method builder. So second attempt, let me try again. This time without curse words. So we go into the start. I won't wait for 10 seconds here, let me just continue on this path. And as you can see, we sort of like managed to go through this and we're returning the task. And guess what? The task hasn't completed yet, it's waiting for activation. So now my caller can move on with its life, right? Like, the task is asynchronously doing stuff. Eventually that thing will complete, but we haven't called set result yet. Now when I hit F5, after a couple of seconds, I did 10 seconds, right? Is that 10 seconds active time or 10 seconds in total? I don't know. Let's hope it's 10 seconds, under the debugger. Because otherwise something is not quite working here. But eventually, oh, I didn't set a breakpoint, damn it. I should have set a breakpoint over here. Let me do it one more time. F5. First state, it runs, the task is returned. Now we're waiting for 10 seconds. Indeed, there was a 42 already staring me in the eye to say that it was completed. Now I'm waiting for 10 seconds, so I'll just shut up. Okay, here we go. State equals 1. We've re-entered this move next method. How did we end up in that move next method? Well, we called await unsave uncompleted, which registered the rest of the async method with the awaiter. And if we look here at the call stack, we see all the way at the bottom that the app domain timer callback fired, queuing something or executing something on the timer queue, going all the way to task over here to finish the task. That was the task.delay, as you can see. And then finally, it went all the way into the async method builder that registered interest in the eventual completion of that task. And we ended up back in our move next, where we correctly remembered here that the state needs to be 1. So at this point we can finish and actually return 42. So that's really all there is to know about the state machine stuff, is like think about the method as having a bunch of awaits and just chop it up in pieces. Everything before an await is one state, everything after an await is the next state. Now of course this is kind of a trivial case because I didn't await in the middle of a loop, or I didn't await in the middle of a using statement, or God forbid inside a try-catch finally, which is even more complex to get right. But the basic idea is actually the same. Just chop up the method into different pieces. So we can take a look later at something a little bit more involved, but let's actually go back over here and choose an entree now that we sort of have the mental framework of async methods under our belts. So there are two things that are quite similar here, like that have to do with custom awaiters and awaiting.NET events. Maybe we can have even two entrees. I think we have enough time. So please. What? Configure await. Okay, yeah, that's actually a good one. Let's talk about configure await, because that's where things get really practical, actually. So configure await. Let me go back to the code over here and show me one thing that could either be a sin or something I'll be forgiven for. In this case, I'm just awaiting task.delay 10,000. Is that a good thing to do, yes or no? Depends who you are. If you are an UI application or something, that's just fine to do. You just await, task.delay 10,000. When it eventually completes, stuff will re-execute. If you're a library, you may not want to just await something. You may want to sort of put something on there called configure await false. Now, what's the distinction? Like, why would I bother, putting configure await false onto this thing? Well, I typed really fast so that you wouldn't see what the name of the parameter is, but let me actually go back here and show you that this parameter is actually called continue on captured context false. Okay? Now, what's that? Well, if I would do the same thing in a UI application, and why not, let me just create the simplest UI in the world using Windows Forms, then I can show you what the problem would be if things wouldn't be working as expected. So let me do WinForms here. And the reason I'm using WinForms is just like, it's a little bit easier for me to deal with that stuff. I worked on WPF and, I never got the hang of it. So here we go. We have a button. And in that button, I want to, that's just a joke, by the way. I just like to have control over all the code generated so I can even step through a whole bunch of things inside the generated code if need comes. So what I will do here is await task.delay 1000. Or, yeah, well, actually, 1000 is enough. Yeah. Now, you could think of this as like, is that not the same as doing something like continue with task goes to, and then over here start doing some stuff, like say button one dot text equals done or something, right? Is that the same thing, yes or no? Well, the answer is it's not really the same thing. In this case, I don't want to do that. So here we go. Let me actually run this thing and set a breakpoint over here and see what's going on. When I click on that button, after 1 second, the continuation of the task has been scheduled. And if you take a look now at the bottom here on the threads window, we are actually on a worker thread. And worker threads are not the best place to update UIs, as you know. If I hit F5 here, things will actually complain. Well, actually, they didn't complain this time, likely because I don't have my managed debugging assistant enabled. But this thing should complain about like, oh, you're trying to update this thing from like a different thread than the UI thread. And so the way that actually the await gets around that is by capturing the current synchronization context. Like the way you would actually get out of this problem is by doing this.invoke, as many of you know, posting things back to the UI thread by, doing this whole charade of things, right? You have to basically call this.invoke so that the delegate gets queued up in the message loop, and then the message loop will pick that thing up and run it under the UI thread. That's the way to do, thread-safe operations on UI threads. And you've seen that many times when you're dealing with the classic async pattern, right? Like, you do begin, or what is it, like begin read and end read, and, the callback comes on a different thread, and you're updating the UI and you're toast. So that's the whole pattern that you have to do. Now, when you do await task.delay 1000, the thing it actually captures for you is the synchronization context. What it's really doing is the following. It's almost as if, let me copy this whole thing, or actually let me just type over here, private void the other method that I had initially, like it's almost as if you're doing this. Before the task.delay starts, we do synchronization context dot current, and we stash it away in a variable. And then when we continue and we're sort of done with the await, this thing would do continuation or context.post, passing in the sender post callback that effectively takes in this piece of code that you can see over here. So that's just a generalization of doing this.invoke. In fact, all the synchronization context for Windows forms will do is actually do pretty much the same thing as this.invoke does. And I've just messed up a couple of things here. I think this thing takes in a parameter, something like that, you know, whatever. Yeah, that's what it is. So as you can see, like that's really what it compiles into. Well, not really what it compiles into, but what the awaiter is doing behind the scenes is capturing the current synchronization context and continuing. Now, what's the problem with that? There is no problem. If you're a UI application or a Windows Forms application or a web application in ASP.NET, that's what you want. You want to continue where you started. So that's very, very convenient. However, if you start having library methods that basically trigger this particular kind of pattern, you may end up in some trouble. And here's an example of that. Public async void foo async, okay? And in here, I'm just gonna await something, you know, that runs on, say, the UI thread. You know, like I just wanna do something here, like this task.run, return 42 or something, and let me, you know, well, I could spend some time here, you know, like, let me just act like I'm busy, you know, I'm doing something. So, you know, something is happening on the thread pool, it's doing its stuff, and eventually this thing will complete by means of an await. And as you can see, I'm not doing any configure await. That means this thing wants to continue on, guess where? The synchronization context, right? It wants to make sure that all the code after this runs on the place where it started from. Let me just do console write line here to do something, you know, and then let me return 42 from here as well. I'm just writing uttermost nonsense here, but assume that that's a library that's doing something, downloading from the internet, trying to calculate stock quotes, whatever, right? So that's in a library. Now, what's the danger? Some UI people still don't understand, you know, all of this await stuff very well, and they may simply call this fooasync.wait or fooasync.result. You know, I don't want to await that stuff, you know, I just want to block for it, okay? So I'm going to block for this thing, and I'm going to then go and do button1.text, .text equals toString of the result. Now at that point you're toast. Why are you toast? Let's actually walk through it. This is the UI thread. The UI thread is calling fooasync. So far so good. Happy walk in the park. We go through fooasync and this thing says, oh, I need to await something. So let me capture the synchronization context. That's good. Synchronization context is captured, and now on the background thread we are starting to sleep for 10 seconds or do some heavy work, and eventually that thing returns 42. Now, at that point, this async method returns, right? Async method returns because it's awaiting something that's not done yet. It takes a long time to execute that piece of work. So we return the task to the caller, and this guy on the UI thread is now happily saying, let me actually block for the eventual outcome of that. So I'm blocking the UI thread. Now this guy, after 1 second, finishes, and the await says, well, I captured the synchronization context where this console write line needs to run on, like where I need to continue from. I need to post the rest of this method to the UI loop, to the synchronization context. But that thing is blocked for the other guy waiting. So the rest of this async method never returns, or never can run, because it's queued up on the message loop. It's sitting there, but somebody else is blocking on top of me. Now, what do you want in this case? Like this fooasync is the one that will unblock the guy in front of me. So I'm deadlocked. Like the guy in front of me is waiting and this guy can't complete because we need to have that synchronization context back. So that's a deadlock. Like, you know, this thing will never finish. So if I would actually execute this, well, if there wouldn't be build errors, an underscore. Oh, I already have an underscore somewhere. Well, I don't need this thing anymore. Control-KC. Fine. So when I click on this button, you know, I'm lost in paradise. Like this thing, I can't drag it anymore. It should only have taken 1 second of blockage. Like even if I'm a bad guy here, you expect only to be bad for 1 second because I'm waiting for something of 1 second. But no, like it's infinite in this case. And that's because like this async awaiter can't complete. It's just like queued up its stuff into the UI thread. How do I get rid of that thing? WinForms. Boonk. Done. So what can you do to avoid that in libraries? Well, be a good citizen. You are not threadifying here at all. like this console write line or whatever you were doing here, like you don't care where that's running. It doesn't need to be on the UI thread. You're a library that's not about UI programming, for example. So if you're just a library, stick configure await false on there. Now what does that do? If we go back to this other method here, it basically gets rid of this part, those parts, and that part. It just does almost what you're seeing over there, like configure await, not configure await, continue with whatever the user wrote as the last part or the next part of the async method, wherever that's running. So the rest of this method here, after the await, will just run where that task completed, which will be the thread pool. This stuff will run on the thread pool, 42 will be returned on the thread pool, the task will complete from the thread pool, the guy who's blocking will get unblocked because, you know, the thing that unblocked it was not scheduled onto the synchronization context. So if I do Ctrl F5 here and I click on the button, you know, I'll be stuck for 1 second, but then 42 comes out. So long story short, there wasn't a good default to pick. If we pick the default of configure await by default capturing the synchronization context, then, you know, libraries could be in this situation where, well, you know, they're picking something up from a synchronization context and God knows who they're blocking. Or who they're working with that's not fair to them. If we would say like, well, by default, we don't want to continue on the synchronization context we captured, then UI developers would be unhappy because they have to do half of the work that they were doing before. You're doing something asynchronous, it completes on a background thread, oh, you get cross-thread violation on the UI framework and you have to do this.invoke again and all of that stuff. So the selection was made to make the typical scenario of building a UI application or a web application and doing a whole bunch of things like awaiting a web client to make that as friction-free as possible. But if you're building libraries, then it's a good pattern to actually put configure await false on the things that you're awaiting. Okay, so and that makes sure that your library composes very well in whatever evil, you know, jungle that it sort of arrives. In this case, the evil jungle is some, you know, noob over here blocking for a task, which should be a sin that's punishable, but unfortunately it isn't. So that's configure await. Now, the interesting thing is that if you look at configure await, what does that thing return? Configure await is a method on task or task of T. Originally in the CTPs it was an extension method, but now it's actually a method that just lives on the task. Now what you can see here is it returns a configured task awaitable of T. What's a configured task awaitable? Well, it's just something that has a getAwaiter method. And what does the getAwaiter return? It returns a configured task awaiter. And what does that one have? Well, it has a couple of methods over here. This is all the compiler needs for you to have something awaitable. You just have to implement getAwaiter, is completed, getResult, and implement either of those two interfaces, iCritical notify completion or iNotify completion. The first one is the optimized one, which has to do with not having to flow the execution context because the async infrastructure can already flow the execution context. Now, I'm mentioning a different word here. Talked about synchronization context, now I'm talking about execution context. What's the execution context? Well, that's the thing where a whole bunch of other information lives. Information like, you know, security stuff and whatever, that sort of has to stay with your logical thread of execution. That thing has to flow anytime. Synchronization context is just a convenience to land on the right thread and do stuff. But execution context contains critical information. So that thing, you can't avoid flowing. It's always flowing, the framework takes care of it, so that you don't lose any of the original context. But synchronization context is a thing that with configure await you can actually suppress flowing and causing like all those kind of deadlock situations. So let me actually serve you a second entree just because it's that fun and very quick to do. The second entree is actually how to build a custom awaiter. Let me just build a very simple custom awaiter for buttons. Okay, so wouldn't it be nice? I'm trying to find like where it would be nice in the context of this sort of semi-silly application, actually super silly application. Wouldn't it be nice if over here in my form, well, not in the constructor, but let's say in here private void setup or something, that I could declare some workflow and I'm using async void here, which is one of my sins today. But wouldn't it be nice that over here in this setup method, I could declare some kind of workflow that the user has to go through in my application to achieve something? So for example, say that I have 2 buttons here, and let me start by making the first button enabled and the second button not enabled, okay? And really what I want the user to do, maybe this is a little game or something, I want the user to click on the first button to unlock an achievement, then the second button becomes available, you click on that one, and then you're greeted with a text box or a message box. So you want to await when the user clicks that button, okay? You want to await when button 1 is clicked, then you want to enable the second button, then you want to await the second button being clicked, and then you'll do messagebox.show, okay? Now, you could do that with regular event handlers, right? Double click on both and have some global state in your form and whatnot. But I want to be able to do this. Await button 1, do button 2 dot enabled equals true, await button 2, and then do messagebox.show well done, not swell done, whatever. So here we go. Now, okay, I was already concerned that it worked, but here are the red squigglies. It says you can't await the button. Button is not awaitable. Guess what? We can make a button awaitable quite easily. What I want to do is have this button have a getAwaiter method. That's the first thing the compiler looks for. How can I do that? Well, I could simply create a static class extensions, public, static. Let's start with void, and then I'll fill it in just a moment. Let me create an extension method on the button, button B here, that does getAwaiter. In fact, let me make this getAwaiter too for just a second and take a look over here. Await requires that button have a suitable, that's kind of weird, have a suitable getAwaiter method, okay? So let me actually uncomment this thing and see what it says. Ooh, that's nice. It does not contain a definition for getAwaiter or not an extension method getAwaiter accepting first argument, yada, yada, yada. Yeah, I kind of have, but the message is already sort of morphing to something else. It's because this thing returns void. It needs to return something. So let me return it a foo, okay? Now let's take a look what it complains about now. Kind of, well, it's still not suitable. Okay, not perfect. The messages are not the best in the world. But what does this foo have to have? It needs to have the notify completion interface implemented. So let me implement that one, like this. And then I also should stick on that. At some point, this thing will start giving more interesting things. Oh, it was sort of thinking about it. Apparently, the getAwaiter is not accessible due to its protection level. Okay, well, this foo needs to be public over here so that, it can see that one. Let me just, make all of those things public, assume that they're in a library. This thing, will eventually come to senses and start, telling us that everything is okay. Now, I have uncompleted. I could wait a little bit longer. The messages tend to become better after time. Yeah, here we go. It's now saying you don't have an isCompleted property. Oh, very good, like public bool is completed, with a getter. Perfect, get. And let me say return false. We'll never synchronously complete awaiting a button. Like nobody can be clicking the button while we're waiting for it, okay? Like it's always going to be asynchronous. So we're never completed at the point the awaiter will ask, like, are you done clicking yet? No, there's no human here, like, shut up. Second thing is get result. Oh, I need to return get result. Beautiful. This thing, awaiting a button shouldn't return a value. Actually, it could return a value. It could return the point where the button was clicked if you want to get the location or something, like if you want to be really fancy. But let me just say that a button, when you await it, the get result is empty, okay? Now at that point, is it almost happy? It's happy. It's doing something, other than the fact that my implementation doesn't do anything useful. But you see the red squigglies are gone. You can await a button by creating an extension method, implementing the interface, adding isCompleted, and get result. So what do I do in order to make this work now? Well, the only thing I really need to do is, let me create my foo here, return my foo, and now do b.click plus equals foo dot done or something. Okay, so in foo, I will have another method here, could be internal, doesn't matter really, done, which will be signaled when somebody clicks the button. So what will I be doing in this one? Well, in fact, let me, this thing needs object sender and event RxE. Object sender, event RxE. Let me actually move this stuff into the method itself, or into the type itself by creating a little constructor here. So let's put the button inside the form here, because I will need to unhook the event handler at some point. I'll just add up my done method over here. In the done method, I'll be a good citizen and remove myself from the event handler. So when you start the waiting, I attach an event handler to the button. When the button gets clicked, I detach the event handler. And what do I do over here? Well, at that point, you need to call the continuation that was passed into uncompleted. Okay? So where will I store that one? Let me store that in a field here. Continuation equals the continuation. Here we go. Actually, I could move all of that stuff in there. That's even better. Let me move that stuff in here. Much nicer. So I'll set up the continuation like this into a local field. There we go. And then when we're done and we've unhooked our event handler, I can invoke the action that was given to me. And that will ultimately call the move next and move the state machine forward. So when you start the waiting, the compiler will, or the code executing will ask, are you done yet? We'll say no. Then it will say, well, here's when you're done, call me back with this particular action delegate. So we'll end up here. We'll hook up the event handler. When the event handler is clicked, we'll trigger the continuation, and that will cause my method to continue. So let's take a look at whether this indeed works. Let's set a breakpoint here in setup, set a breakpoint after the first to wait and at the message box.show. So let's hit F5. Here we go. My form is running. It hasn't shown up yet, but I should really do it in the load method or something. I'm awaiting the button. The first thing it does is get the waiter, which returned a foo, and now it's asking the foo, are you done yet? We're saying, no, we're not done yet. So the next thing is, we're given the continuation. When you're eventually done, please invoke this continuation to resume the execution of the async method. If I would drill into that with some debugger over here, well, actually you can see it over here as well. I was thinking I need WinDebug here to go a little bit deeper, but it sort of leaks the target of the delegate here. You see that the delegate is the async method builder core continuation wrapper. That's my async method builder saying, please call me back here, and I'll make sure that the state machine moves forward. So this thing is setting up the button click handler, and we're done. Now we're waiting for the user to click the button. If I click the button, my event handler runs, and I'm calling the continuation. What does the continuation cause us to do? We're back in the method where the await happened. So now button 2 becomes enabled, and I'm awaiting the second button, which is not clicked yet. So the continuation is given to me on our way to the message box.show. When I hit F5, we see the second button is now enabled. When I click the second button, we await. The continuation that was given to me gets invoked, and we end up with message box.show, well done over here. So now I've encoded a workflow in a UI using this. You could be awaiting a text box containing a valid IP address or something, like await based on a text change, and until that thing is not returning the right thing, then I won't enable the next UI element. So all of your logic now can be really together condensed in a single method, as opposed to having a whole bunch of fields to keep track of where you are. You're effectively building the same state machine as that the async method builder is creating for you. So that's a little trick that you can apply to make any of your types awaitable, where it makes sense to asynchronously wait for something, whether it's a machine or a human that you're waiting for. In this case, I'm waiting for human interactions. So await goes all the way to social interactions. Did you ever believe that? All right, so in fact, I've given you quite a few things there as part of the entrees. We've talked about configure await. If you're a library, stick configure await false. Otherwise, you may deadlock somebody because you're posting back to the same synchronization context where somebody else may be blocking on. So that could be a little bit of a problem. We talked about building custom awaiters, and I actually showed you how to await .NET events. Let me actually pick one more entree, and then I'll ask you what the dessert should be. I'd like to talk very briefly about stack spilling, because that's one of my pet peeves. It's one of those things that when you look at this code, what the heck is the compiler doing here with my code? It looked so innocent, and it turns into that dragon of IL code here. The reason for stack spilling is that await expressions are, I've already mentioned it, expressions. So let me show you something. If I go into, let me go into my state machine demo over here, and let me just create a second method, static async task of int bar async. I'll run out of those names eventually. But what you can do here is like you can await, say, task from result, which is nonsense because like task from result returns a task that's already done. But I can await task from result 42 or await like, you know, some web request or something. Now this whole thing is an expression. This thing is something of type int. What can you do with something of type int? Well, you can multiply it times 2, for example, and you know do console write line of that thing, right? Console write line of 2 times the result of awaiting something. I don't need the parentheses in this case. But this is totally fine. Await is just a unary operator that returns, let me return something here, that returns whatever the type is that the getResult method of the awaiter returns. Like in this case it's task of t, and the getAwaiter getResult returns a t. Like if that thing would return something else, that would be the result of the outcome of awaiting something. Now, because of that, you can end up in this interesting situation where you are in the middle of evaluating an expression, like you've computed the value 2, big achievement to get the value 2, and then you're multiplying it with the from result result. Now, what if this thing pauses? Like say that it's not just returning synchronously in this case, but say it's going to the website or something. Well, at that point, everything that's on your evaluation stack should not be lost, obviously. Now, 2 is a constant. You could say, we can recompute that thing. But say that in this case, you do console.readline over here, .length. So, like you ask the user, please give me something. And that thing has a certain length. And now that length, we've computed that. We can't ask the user again to enter like, some text and get me the length. We have that length sitting on our evaluation stack. And now the rub happens, right? Like we're calling task from result, we're asking, are you completed yet? And can you believe it, that thing says, I'm not done yet. Now we're sitting there with that hot potato of the length of the user's input on our stack. What do we do with that? Well, we have to store it somewhere because we have to return to our caller. It's sitting on the stack. We need to store it on the heap somewhere. Now, this is quite easy in this case. Like it's just one local variable or something. You could say like, we can just store that in a field. But of course, I could be more evil. What if this thing asked for a second one? Well, in this case, it's still the same thing because, multiplication is left associative by default. So it will compute the multiplication of the 2 lengths first and then, await. But what if I make this thing, it's just an expression. So like, I can just be crazy over here. What if I do it like that? Ask the user for some input. Ask the user for some input again. Now we have 2 things on our stack and we need to multiply the last one with 42 before we can multiply that one with the other length that we got. So this thing can grow as long as you want, and the side effect should be left to right. You want the first input to end up here, the second input to end up there, and then the result of the task to happen over there. Those things can't be reordered because you're dealing with the user here or there may be side effects. So that's where stack spilling comes into the picture. Now let me make it a little bit simpler here rather than console readline or something. Let me just do task int f. That returns after a while some value which may be different every single time. Imagine that this thing is not here. Well, why not, Let me just move that thing over here. Beautiful. Will not be the same. Well, hopefully. So here we go. So I can be evil here, right? You can already see how I can be evil, Very evil. Well, I hope it's the right number of parents. It's not the right number of parents. Damn it. 2 more expected, it says. Yeah, very nice. So this looks like quite a hell of a thing with a whole bunch of intermediate results and then we're awaiting. Can you imagine it? We need to store all of that stuff. So when I build this and I go to, let's do ILSpy for this one, and we inspect that code for just a moment here and see demos.stateMachineDemo, and we go to bin debug stateMachineDemo, and we unravel this one here. What I've done is under the view menu options, I've disabled decompilation of async methods. If I turn on the decompilation of async methods, we don't get to see what the compiler generated really, and we can see in Well, actually, we start generating different code in C# 6.0, so this thing is kind of completely busted now in ILSpy. We changed the pattern ever so slightly to support, catch and finalies with awaits in them, and ILSpy is kind of upset about that. So I'll have to really show you what the compiler generated here. But otherwise, you would just see the code that I was writing here in Visual Studio. It would correctly decompile f times f times f with the parentheses in the right place. It's not doing that, which is good, because I want to show you what it's really generating. And in fact, okay, something changed in Roslyn in the current thing. It's not doing the stack spilling. Oops, like little. That's a little bit okay. Yeah, I should have known that that this thing was running this particular build. Let me show you stack spilling by recompiling my app on the command line. Here we go. Let's go here, copy full path, and then ILSpy will be happy with me again. I think the stack spilling will come back, actually. I'm not entirely sure where the status of that is. But what I was running was rcsc, which is the Roslyn C# compiler, on program.cs. And in fact, it's not registered over here. But that's the one that got actually invoked. I will just do csc of program.exe, which is the C# 5.0 compiler, as you can see over there. So that doesn't contain the Roslyn bits yet. And when I open up this guy now, we can actually see the difference. Program.exe. Let's start off by taking a look at the wrap over here, not the wrap, at the async state machine, or the async implementation here. We see it's quite different. I can explain later what those wraps are for. But when I go back to decompile the async methods here, for my program.exe, we should see that indeed it correctly decompiled it. It didn't get confused by the old code. It needs to be educated about what Roslyn is doing. But this looks good. Now, how did the compiler generate that? Well, if we take a look over here in the async state machine, and we take a look in the move next method, we see that indeed we're evaluating program.f, how many times, I don't know how many times here, looks like 10 or something, or 9. So we're evaluating it a bunch of times there, it's 10, before we have to call the getAwaiter on our task.from result, which could take a really long time to complete. So if we are eventually done with that thing, we want to have all of those results back. We can't call f again, right? We need to store the results that we already got before we entered the await state. So what's happening here is what's known as stack spilling. Everything over here that's local variables get actually packed up in this big-ass nested tuple. All those values are stored in a big tuple. That tuple is then put over here into an object on the stack of type system.object, because we only need one of those. If you have multiple places where you are awaiting something and you have stuff on your stack, we can reuse that same field. It's always going to contain a tuple, and we can cast to the right one based on where we are in the state machine. So it basically stores that tuple over there, and then eventually we complete over here, we unpack that tuple. Get the things out, store them back in local variables, so we can carry out eventually over here the multiplication. Oh, oops, that's clicking on console right line. But here's the multiplication, as you can see, this whole thing. Now, what's interesting is that if we're completed immediately, which is over here, if we're completed immediately, then we never go to the stack spilling stage. We never enter the else block either, which is doing the unspilling, and we end up all the way here on get result as if nothing happened. It's still all local variables. So everything stays local, that's the general theme. Everything stays on the stack until the rub happens. The rub of oh, we have to asynchronously do something here, we need to pack up our bags and leave. And in this case, it's doing stack spilling. Alrighty, so that's something you may come to see at some point when you inspect the IL code, or look in ILSpy or Reflector or whatever behind the scenes of an async method. What are those tuples for? Well, they're there to deal with the intermediate results of an expression containing an await. All right, so let's see. What can we pick as a light, sort of dessert, or maybe even a new dish? What? Task combinators. Okay, that's a very lightweight thing. Tasks are not free, as you can imagine. I've explained many times here that we try to do our very best not to put things on the heap that don't belong there, like until the point is that we cannot get away with not storing them over there. However, tasks themselves still have a little bit of overhead. Those are heap allocated objects, they're not structs. As you can see, they're classes. And in fact, in .NET 4.5, quite some work has been done to give a task two persona. Actually, task has internally been split up into two types. One type that contains the absolute bare minimal essentials, which is, I don't know how many bytes it ultimately got, but a couple of tens of bytes. And then you have all the rest, which is expensive to allocate. Things like, oh, you go to the task and you want to get a wait handle for it. Like, well, that needs to return an async result object, blah, 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 a whole bunch of things, expensive to create, expensive to allocate, expensive to collect. So those things don't come into existence until you call certain methods on task which are not that common to use, especially when you're using a wait. Those methods are never called. So tasks have gotten a little bit more lightweight. However, in quite some cases, you can avoid doing a whole bunch of awaits on different objects. In some sense, awaits can be more expensive than those lightweight tasks now. Say that you have two things you need to await for. Say you have like, task T1 or something, or let's say, just task, why not? And you have task T2, okay? And then you're doing some stuff. And then at some point, well, it's a fork join algorithm. Like, it's forking to execute task 1 and task 2. And then you need to join at some point because you absolutely need the results of both those tasks. Now, what you could do here is you could await T1 and await T2. And that's kind of fine, but what may be the case here? That both of those guys are not done at the point you're awaiting them. Everything gets evacuated to the heap. A whole bunch of things may be resulting from awaiting those things individually. Now, in this case, I want to wait for both of them to complete. So that's where task combinators come into the picture. You can actually await task dot wait all, or not wait all, when all, and then passing in a params array or an enumerable of tasks. So you can pass in here T1 and T2 and await for both of them to be completed. And after both of them have been completed, you can do T1.result or T1. Well, in this case, there's no result on it because it's task of void, but you get the idea. The red squigglies is just because I haven't assigned anything to them. So we have task.whenAll and we have task.whenAny. We also have waitAll and waitAny. Now the waits are of course the ones that are synchronously and blocking. The whens are the ones that are asynchronous. Now in this case whenAll is quite simple. You see it takes in multiple tasks, which could be task of int because those derive from task as well, and what it returns is a task. So we can await the task that comes out of it, and that will be the task that completes when both of them complete. Internally, that's just implemented using some task continuation or task completion sources. Now, there's also this whenAny call, which is really useful to time out something. That's one of the chief uses of that. So what you can do is, like, say you want to wait for task T1. You'll deal with the red squiggly here, it's just because I didn't assign something. I could come up with something, but it doesn't really matter. So I want to wait when T1 completes or there is a timeout. How can you represent the timeout using a task? Well, you can simply do task.delay of, like, let's say 20 seconds over here. Now, what does that thing return? whenAny returns a task of task. That's where, you may be blown out of your socks or something, but it's not that bad. Like, what does that mean? You can await the outer task, and it will return, as the inner value, the task that has caused the whenAny to complete. So when I await this, I get an object back, a reference to one of those two tasks I passed in, the one that caused me to complete the whenAny state. So when I do await here, and I have task that completed over here, I could check that the task that completed equals T1. Then I know that T1 has completed, and I can await the result of T1 and do the rest of my work over here. Else, I know that it was the other task, the task.delay, that caused this task.whenAny to complete, and I can throw a new timeout exception or something. So that's a very common pattern to use the combinators on task for, is to time out something simply by doing composition. Now, this is pretty similar to wait for multiple objects and wait for multiple objects EX if you were ever doing native Windows development. You know, those guys also have like any or all. You can wait for all things to be set or for any of them to be signaled. And you can also do timeouts and those kind of things with that. So those are the combinators. Long story short, just go to task and dot into it, and you can find some things that are useful, like task.delay, the when any's and the when all's. We also have task.yield. If you know at some point it's kind of okay that you don't have anything else to do, but somebody else may want to do some work, you can sort of yield yourself by awaiting task.yield. And then, of course, you have all of the continuation things which we already knew from .NET 4.0. So that's task combinators. So let's actually wrap up here with the new dishes. You know, I'll have a video online at some point about these. You know, likely, you know, most of this is actually also on my courses at Pluralsight. I still need to do some new recordings of new stuff. Let's actually show you one more thing. That's the exception dispatch info. Chef secrets we talked about very briefly. Execution context, the thing that always flows, you can't get rid of that. And async debugging improvements, well, things have improved a little bit in Visual Studio 2013. Like when you're looking at the call stack of something you're awaiting, it will look more meaningful. So let's just show you exception dispatch info. This is a very little interesting type that lives in system runtime exception services. It's in fact the only thing that lives there today, as far as I know, unless we added something very recently. But what you can do with exception dispatch info is capture an exception with all of its information, stack trace and everything you have, to throw it at a later point. Now that's very critical for things like await support. Because like at some point, inside the infrastructure, we may have an exception object that we caught, and we need to rethrow it, but we can't lose the original call stack. And as you know, in the CLR, you can't really do that. Like if you have try, and you have a catch over here with exception EX or whatever, and you do just a throw, that's fine. You're rethrowing the exception using the original call stack. That's good. But you can only call throw when the exception is still somewhere in the CLR's memory, like, you know, at that point, you know, inside the catch handler. You can do throw EX, but then you lose the original call stack, because whenever you do throw EX, it takes the current call stack, stuffs it into the stack frame of that particular exception, and then throws that thing out. You lose everything that caused you to end up here. So you're out of luck if you need to store that exception somewhere in a field, like error equals EX or something. You need to store it somewhere, and then you need to rethrow that thing as if nothing happened at a much later point in time. Like, you know, outside this catch, maybe asynchronously after something else has happened, much later you want to throw the error over here, which was an exception. Now there's two ways to get out of that. One way is to wrap the original exception in a new exception, right? So that it becomes the inner exception. But like, the user doesn't expect that, you know, if an IO exception happened at some point in your program, and for whatever reason you could not rethrow it immediately, that some other exception would come out, like, you know, my wrapped exception, and find your IO exception inside of that thing. That wouldn't make sense. So with exception dispatch info, you can actually store over here the exception in an exception dispatch info object, and as opposed to doing throw over here, you can do .throw. And that will rethrow the exception with its original stack trace at the point you caught it, as if nothing happened, but it's just coming from a totally different place. And that's something that, in fact, the new async await support for finally blocks, for example, uses exception dispatch info. The compiler will generate code like exception dispatch info.capture. And some things inside the await infrastructure for tasks also use exception dispatch info. So I invite you actually to go in, for example, ILSpy.NET Reflector, the reference source page on MSDN, to actually look for all the uses of exception dispatch info. And you will actually see that this is a very useful type in cases where you have a hot potato of, you know, an exception in your hands and you need to throw it out later. Well, without losing any information, you can use EDI. That's the abbreviation of exception dispatch info. So with that, we've come to the end. We've actually covered more than I expected to cover, so that's always great. Hope you got some some useful tips and tricks out of it. Things like configure await using the task combinators exception dispatch info. I hope you also appreciate like the complexities of the async state machines and all of that stuff. So if you ever find yourself lost in some hardcore debugging session and you want to see like, oh my God, what did the compiler do with my code that looked so simple and so obvious in async methods, now sort of know where to start looking. And finally, well, I hope to see you again some other time to talk maybe about like the new features in Roslyn and how, the continuation of how stack spilling has evolved and, the cruel story of the Lambda and all those kind of things. So thanks very much for your attention and hope to see you again.